Okay, the next chapter we're doing is stoichiometry. Now we start off with mass stoichiometry. Basically, we're just working with masses. Now, this topic is all about calculating amounts of chemicals that react, amounts of chemicals that are produced in chemical reactions. So using a chemical equation to work out the masses that are consumed and produced. So the natural first step then is to just brush up on our balancing of equations. So that's always the first step. You always need a balanced chemical equation to do stoichiometry. Now usually in stoichiometry questions the equation will be given to you, so we'll be asking you to show your ability to do stoichiometry questions in a different place to where we'll be asking you to balance equations. However, we'll just do a little bit of practice now. So when you're looking at a chemical scenario, first of all you need to think about what sort of reaction are we talking about here? And that will tell you what the reaction scheme is. And from that you'll be able to generate a word equation. So name the reactants, name the products, work out their formulas to give you a skeleton equation, and then balance that skeleton equation to get the overall balanced equation. So let's start off with these. I might just work through them here. So the first question, we've got sodium hydroxide reacting with sulfuric acid to produce sodium sulfate and water. What sort of reaction is this? Well, hopefully, especially at this stage, you're all recognising that as an acid-base reaction. So it's acid-base, and what's the reaction scheme? Acid plus base gives salt plus water. And so in this case, I'm just going to go straight to a skeleton equation here. So we know that sodium hydroxide is NaOH. We know that sulfuric acid is H2SO4. Those common acids and bases, it's good to know those formulas off by heart. Now we know what water is, H2O. So that takes up the OHs and the H's. What's the salt? What's left over once we combine the H's and the OHs? Well, we've got sodium and we've got sulfate. So therefore our salt is sodium sulfate. So sodium is 1 plus, sulfate is 2 minus, so that means we'll need 2 sodiums to get the correct formula. So that's a skeleton equation. Now, we can't change any of those formulas. If we're to balance that equation, we can only do so by changing the coefficients out the front of the chemicals. I look at the salt usually as my first port of call, and what do we see? We've got 2 sodiums, 1 sodium. Therefore, we'll need 2 sodium hydroxides. So that takes care of the sodium sulfate. Now we've got 2 hydroxides and we've got 2 hydrogens. That means we're going to get 2 waters. And because we always do, we'll just chuck in a few states. You'll be told when things aren't obvious, when things aren't aqueous usually. Magnesium powder reacts violently with iron 3 oxide to produce liquid iron and magnesium oxide. It's actually a redox reaction. Don't need to do the whole redox aqueous stuff. This isn't actually aqueous, so that's not a valid method. But if we just start off by writing our skeleton equation, we're told all the reactants and all the products. It's pretty easy to work it out from there. So what's reacting? Magnesium powder. So that's metallic magnesium, just Mg on its own, no charge because it's the solid. It's the elemental solid. Is reacting with iron 3 oxide. So that's Fe3 plus. And if you remember all your ions, Fe3 plus and O2 minus means it's going to end up as Fe2O3. Is producing liquid iron. So that's elemental iron again, just iron on its own, no charge. And the magnesium's been oxidised to magnesium oxide. Mg2 plus, O2 minus, means we get MgO. So balance that, what have we got? 2 Fe's, 3 oxygens. That means now we've got ions are balanced, oxygens are balanced. We've just got to go back and balance the magnesiums. 3, and as I was saying before, when the states aren't really obvious, you'll be told them in the question. A powder is obviously a solid. Ionic compounds are pretty much solids. Molten iron, it's a liquid, and the magnesium oxide will be a solid too. Now, equation 3 is a double replacement reaction. We did a little bit of that in our work on water. So we're told the 2 reactants, and we're told what one of the products is. It'll be pretty easy to work out the rest. So one of the products is a precipitate, so we know that's the solid. So calcium chloride. Because we know our ions, we know that CaCl2 reacts with silver nitrate, AgNO3, to produce, as I said, we know one of the products, silver chloride, and what's the other product going to be? Well, the silver leaves the nitrate, the chloride leaves the calcium, so it's going to be calcium nitrate. Hopefully that's going to be visible on the end there, should be. Okay, so we know our ions, that means this equation's pretty easy to, skeleton equation's easy to write, and then the balancing is all we've got to do. So look for the 2. So what have we got? We've got 2 nitrates, that means we'll need 2 of these. 2 chlorides means we'll need 2 of these. And I think that's 2 silvers, 1 calcium each, so it's all good. And let's get those states. The precipitate is solid. Everything else is aqueous. The answers, and then the combustion reaction to finish off with. Let's just do that 1 and 2. We remember from our organic chemistry, hydrocarbon plus oxygen gives carbon dioxide and water. That's our reaction scheme. Now, what's the formula of propane? Hopefully you all remember prop is 3. So propane must be C3H8. Now, our skeleton equation has us reacting that with oxygen to produce carbon dioxide and water. balancing combustion reactions, you remember the steps. First of all, we balance the carbon, so 3 carbons means 3 carbon dioxides. Then we balance the hydrogens. 8 hydrogens, all the hydrogens end up in the water. Each water's got 2, so that means we'll need 4 waters to balance the hydrogens. Then we work backwards to work out the oxygens. So how many oxygen atoms have we got on the left-hand side? 3 times 2 equals 6, plus 4 times 1 equals 10, equals 4, 4 plus 6 equals 10 of course, and 10 oxygen atoms means 5 oxygen molecules. So, that's that. Now we just need some states. Combustion reactions, most things are going to be gases. We assume that it's at standard laboratory conditions, water will be a liquid. And that's the final version of that.